Welcome back to The Explainer. Today, we're diving headfirst into the messy, chaotic reality of data systems, and more importantly, how we keep them from just completely falling apart. I mean, if you're building software, you already know things go wrong literally all the time. Networks drop, servers crash, disks fill up out of nowhere. So today, we are unpacking a really fundamental concept that prevents those everyday failures from totally corrupting your data. Okay. Here's our roadmap for today. We're going to start with the chaos of unmanaged data, introduce transactions to the rescue, break down atomicity and consistency, then isolation and durability, and wrap up by simplifying your application logic. Let's jump right in. Section 1. The chaos of unmanaged data. To really understand why we need these safety nets, we're going to ground this whole explainer in a high-stakes, real-world example that pretty much everyone understands: a bank transfer. Normally, moving money feels like one seamless action to us, right? But to the database, it's actually a sequence of multiple distinct steps. Think about it. First, it has to check the balance of account A to make sure there are actually enough funds. 2, it subtracts that money from account A. And 3, it adds that exact same amount to account B. Pretty straightforward. But here's where we hit that messy reality of computing. What happens if a hardware fault, a sudden network blip, or a complete server crash happens right in the middle of that transfer? Specifically, what if the system goes down right after it subtracts the money from account A, but before it can add it to account B? Well, without a safety net, you get absolute chaos. I'm talking missing money. The funds left the first account but never arrived in the second. You end up with inconsistent balances that just don't add up, duplicate records if the system tries to blindly retry the whole thing, and weird partial writes just sitting there in your database. Suddenly, your entire application is completely untrustworthy. It's a nightmare scenario. Section 2, transactions to the rescue. And this brings us to the ultimate fix, the real hero of our story here, the database transaction. This is the exact mechanism databases use to bring order to all that chaos. Think of a transaction as basically a protective bubble. By definition, it's a way for an application to group several reads and writes together into a single indivisible logical unit. It guarantees that a cluster of data changes either succeeds entirely or fails together as one unit. There's no halfway. It is totally an all-or-nothing proposition. Now, for you software engineers watching, this actually translates to very specific code syntax. We wrap our queries right between a begin transaction and a commit statement. And that tells the database exactly what operations belong together inside that protective bubble. If something goes sideways, the database just issues a rollback, essentially undoing everything inside that block like it never even happened. Section 3, atomicity and consistency explained. Okay. Let's break down the famous acronym ACID. This describes the exact safety guarantees that transactions provide. We'll start with the first half to see exactly how it protects that bank transfer we were just talking about. So the A stands for atomicity. In the database world, atomicity is the absolute guarantee that if an error happens partway through, the entire transaction is aborted. All operations commit, or absolutely none of them do. This is what saves us from those terrifying partial failures. If step 3 of our bank transfer fails, step 2 is entirely discarded, the money is returned to account A, and honestly, it's as if nothing ever happened. Imagine a timeline where a user starts inserting data and then updating another record, but right in the middle, bam, an error or timeout occurs. Because of atomicity, the database doesn't just leave that first insert hanging out there in the void. It actually rolls back the previous steps to maintain a consistent state. The best part? You don't have to write complex error handling code to reverse the partial write yourself. The database just handles the whole shebang for you. Next up is the C, which stands for consistency. Now, there's actually a super common misconception here. Consistency isn't really a property of the database itself. It's an application-specific notion. It's all about preserving your specific business rules or invariants. For our bank, the rule is that the total amount of money across all accounts must be exactly the same before and after the transaction. The database gives you atomicity to help you achieve that, but defining what consistent actually means, that's entirely your application's job. Section 4, isolation and durability explained. All right, let's move on to the second half of our acronym and tackle the really tricky problems of concurrent users and catastrophic system crashes. The I stands for isolation. Imagine our bank transfer again. What if two different users try to transfer money out of the exact same account at the exact same millisecond? Without some help, they might both read the same initial balance, bypass the limits, and withdraw double the money. Isolation is what ensures these concurrently executing transactions don't step on each other's toes.
The crucial takeaway here is this stark contrast. Without isolation, you're looking at race conditions, dirty reads, and ultimately missing money or corrupted data. But with isolation, the database organizes these concurrent transactions so seamlessly that it actually lets us developers pretend concurrency isn't even happening at all. Even though they execute at the exact same time, the end result looks as if they ran sequentially, just one after the other.
To really grasp what happens when isolation fails, let's look at what's called a dirty read. Let's say user 1 is right in the middle of a transaction, writing new data. But before user 1 commits, user 2 queries the database and sees that uncommitted, half-finished data. If user 1 then hits an error and rolls back, well, user 2 has now made decisions based on data that technically never existed. Proper isolation levels in a database completely prevents this exact scenario. Finally, we get to the D in ACID, which stands for durability. And this is the ultimate promise. Durability means that once the database tells your application, yes, the transaction has committed successfully, that data is safe. It is permanently recorded on a non-volatile disk or in a write-ahead log. Even if someone literally trips over the power cord and unplugs the database server a millisecond later, that bank transfer is safely recorded and will be right there waiting when the server boots back up. Section 5. Simplifying your application logic. Let's pull this all together and look at why this matters so much, especially if you're just starting out in system design. There's a really foundational principle that sums all of this up. Transactions were created with one primary purpose: to simplify the programming model for applications accessing a database. That is the huge takeaway here. Transactions are an abstraction layer. The database takes on the incredibly difficult burden of managing concurrency, preventing race conditions, and handling crash recoveries. Why? So you, the developer, don't have to write thousands of lines of complex error-handling code just to safely move money from point A to point B. It's a massive relief. But I'll leave you with this final, kind of provocative thought. Everything we've talked about today works beautifully on a single database node. But what happens when your system scales way up? If a single database relies on its own hard drive to promise these ACID guarantees, how do we maintain atomicity and isolation when a single transaction needs to span across multiple, geographically distributed databases all over the globe? That's where things get truly complex, and that is exactly what you should be thinking about as you design the next generation of data-intensive applications.